Hello, AP Statistics. Welcome to section 11.1. In this section, we are going to be studying Chi-Square, as Chi, C-H-I is Chi-Square tests for goodness of fit. Terrible name. All right, by the end of this section, you should be able to state appropriate hypotheses and compute the expected counts and Chi-Square test statistic for a Chi-Square test for goodness of fit. You should be able to state and check the random 10% and large count conditions for the Chi-Square goodness of fit test. You should be able to calculate the degrees of freedom and p-value for a Chi-Square goodness of fit, perform the Chi-Square goodness of fit test, and conduct follow-up analysis when the results of a Chi-Square test are statistically significant. So basically what we're dealing with in Chi-Square is a whole bunch of proportions at once. So here's an example. Here's what the Consumer Affairs Department of Mars Incorporated says about the distribution of color for M&M's milk chocolate candies produced at its Hackettstown, New Jersey factory. And so we have a whole bunch of proportions. Proportion brown, red, yellow, green. This is the distribution they claim. Jerome's class wondered if the distribution of color in a large bag of M&M's milk chocolate candies differed from the claimed distribution. And so they've got a sample here basically of 60 candies from that bag, and here are the actual count that they got. Out of their 60 in their bag, they observed those amounts. So yeah, we can check and see if the proportion exactly matches, but we want to think about it as just sampling variability. But we don't want to focus on a single proportion at a time. We want to focus on kind of all the proportions, in fact, the entire distribution, and that's what Chi-Square lets us do. So our null hypothesis is that the distribution of color in the large bag of M&M's milk chocolate candies is the same as the claimed distribution, while the alternative hypothesis is that the distribution of color in the large bag of M&M's milk chocolate candies is not the same as the claimed distribution. So you could write this in symbols as well. Oftentimes you also are allowed to write your hypotheses for Chi-Square in words like this. But if you wrote it in symbols, it would look something like this, and it gets kind of long. So you could say proportion of brown is 12%, proportion of red, and so on and so forth, yellow, green, orange, blue. So we have all those proportions match what they claim. And then the alternative hypothesis is that at least two of the proportions are incorrect. Because if one's incorrect, then another has to be incorrect. So that's kind of why they say that. But that's in the same way as saying that the distribution is not the same, that those probabilities are not the same. So where, and they kind of get general with this, you could define each one differently, but they just said P sub color equals the true proportion of M&M's milk chocolate candies in the large bag of that color. So caution, do not state the alternative hypothesis in a way to suggest that all of the proportions in the hypothesized distribution are wrong. So it's not that all of them aren't equal, it's that at least two of them are not equal. So how many candies of each color should Jerome's class expect to find in their sample of 60 candies? And so if we take each of those proportions, so they expect 12.5% of the 60 in their sample, so they expect 7.5 of each of those, even though it's not actually possible to get, well, I don't know, it depends on how you're counting M&Ms, but a half an M&M that's brown. And so on. Green was the same percent, but then orange and blue, a little bit more. We expect a bit more. So those would be the expected amounts that we would expect in our sample. So calculating expected counts in a Chi-Square test for goodness of fit, the expected count for the category I, so they like the first category or the second category. You can do this a bunch of times. Like this would be N1 times P1 and so on and so forth. Or I guess it's just not N1, N times P1, N times P2, so on by each proportion. So the expected count for each category in the distribution of a category variable is N times P. We just take the N times that corresponding probability or proportion, where P sub I is the relative frequency for category I specified by the null hypothesis. So basically just multiply by each proportion to get the amount that you would expect. So then here's a little quick analysis of what was observed versus what we expected. And so we can see that the observed that, yeah, the brown, we got 12, we were only expecting 7.5. We didn't get as many red as we expected. We got more blue than expected and so on. So you can see that here in these observed counts. versus the expected counts. So what we want to ask ourselves is, how likely is it that the differences this large or larger would occur just by chance in random samples of size 60 from the population distribution claimed by Mars? So we're not going to just focus in on it one at a time. We could do a one proportion test for this and see, but we're going to see, like, overall, combining all of this together, how likely is it that we would see that much difference? And so the test statistic that we use to make this comparison is the chi-square test statistic. This is a little Greek symbol. It looks like an X, but it's kind of like a squiggle X. That's the symbol chi. That's the Greek letter, and then squared. And it comes from this formula here. So the chi-square test statistic is a measure of how far the observed counts are from the expected counts. The formula for the statistic is observed minus expected squared divided by expected. So this kind of gives us like a distance away, but it could be positive and negative. If we just add all those up, it'll cancel out. So we have to do something to make it positive. We could do absolute value, but we don't like absolute value. So instead we square it like we've done before. But then we want it kind of relative to the like how much we expected. Like, is being off by 100 a lot, or being off by 10 a lot? Well, it kind of is relative to the size of the number we're talking about, and so that's why we end up dividing by that expected and sum all that up. So it's like a proportion almost off, but it's the squared kind of throws that off. Where the sum is over all the possible values of the categorical variable. So so this would be how that would look for this data. We had our observed minus expected squared over the expected count there, and so on and so forth. So we add those 6 terms, and we'll get a single chi-square value. So overall, this is like kind of like an amount off for each value. We end up getting a chi-square value of 9.8. So if we look back through our categories, for instance, our third category doesn't contribute that much at all because our observed is very close to our expected. So that doesn't contribute much to this chi-square test statistic. However, the categories that cause more here are like the first couple, where we're off 12 and we were expecting 7.5, and then 3 we're expecting 7.5. Those are kind of both the same amount off, if we think about that. And then another thing to think about is like how far that is away. It is kind of relative to what we expected. Like being off right here by, what would that be? So that's 4.5. Being off by 4.5 when we were expecting 7 is kind of bigger than when we were expecting 15. If you're expecting 100, being off by 4 is not that big of a deal. So that's where this relative component comes into play here. And we see that this is not as big of a component to this chi-square value as this one is, even though that actual difference is larger. All right, so for example, we're going to calculate the chi-square test statistic for a problem. Carrie made a 6-sided die in her ceramics class and rolled it 90 times to test if each side was equally likely to show up. The table summarizes the outcomes of her 90 rolls. So she had the possible outcomes 1 through 6 and how many were observed out of those 90. State the hypothesis that Carrie should test, and we'll go on from there. So the null hypothesis is that the sides of Carrie's die are equally likely to show up. The alternative hypothesis is that the sides of Carrie's dies are not equally likely to show up. You could also say that the probability of a 1 is 1/6, and the probability of a 2 is 1/6, and the probability of a 3 is 1/6. There'll be another way you could write that out. But we can just kind of say it this way, that they're all equally likely, and that they're not equally likely. At least 2 of them are not 1/6. So the part B says calculate the expected count for each of the possible outcomes. So we're going to go with 1/6. So if the null hypothesis is true, each of the 6 sides should show up with 1/6 of the time. So the expected count is 90 times 1/6 for each one. It's 90 times 1/6 for all of them. That's, in this case, since it's supposedly a fair die, they're all expected 15. We didn't observe 15 across the board. That's what we expected for each of those. And so then calculate the chi-square value of the chi-square test statistic. So we would go through each observed value, 12 minus our expected 15 squared over 15, and then 28, that's going to contribute the most there. That's a big component of that chi-square value, and so on. And so go throughout all of those 12, minus 15, 13, and so on and so forth. So this number here, this chi-square that we get, that measures kind of how far off that value is. You know, how far off our observed data is from what we expected. And so the next section we'll kind of look at how, you know, how likely is that to happen, and we'll get a p-value from that.